Right now, 300 miles off the Oregon coast, something impossible is unfolding in absolute darkness. The ocean floor itself is swelling, rising, deforming under pressures that have exceeded every threshold scientists use to predict volcanic catastrophe. This is not a drill. This is not a distant threat. The most active submarine volcano in the northern Pacific has entered a state that researchers are calling maximum alert, and the implications stretch far beyond the deep ocean. What happens when billions of tons of magma push upward beneath 1,400 meters of seawater? Why are scientists watching this volcano more closely than any land-based system in North America? And what does this hidden crisis mean for millions of people who have never heard its name? The danger is real, the timeline is uncertain, and the abyss is preparing to speak. Most people picture volcanoes as towering peaks crowned with fire and ash. They imagine Mount St. Helens or Vesuvius, visible threats that dominate the skyline. But the most powerful volcanic system in the Pacific Northwest does not rise above the waves at all. Axial Seamount sits in perpetual night, buried beneath the North Pacific. Its summit lies 1,400 meters below the surface, invisible to satellites, unreachable by conventional observation. The caldera alone stretches 3 kilometers by 8 kilometers, a crater wide enough to swallow entire towns. For decades, this volcano operated in obscurity. Eruptions came and went without headlines, without evacuations, without panic. Scientists recorded the events in technical journals, while the world remained unaware. But invisibility does not mean safety. What makes axial seamount uniquely dangerous is not its size or its depth, it is its position. The volcano straddles the Juan de Fuca Ridge, one of Earth's active spreading centers, where tectonic plates pull apart at roughly 6 centimeters per year. As the seafloor stretches and tears, magma from the mantle rises to fill the gap. This is not a slow, contained process. It is a perpetual engine of creation and destruction. Most mid-ocean ridges produce steady, low-intensity volcanic activity, but axial is different. Beneath the spreading center lies something far more volatile, a mantle hotspot. This is the same kind of deep earth plume that fuels Hawaii, a column of superheated rock rising from hundreds of kilometers below. The hotspot adds an extra reservoir of magma, a second fuel source that transforms axial from a typical ridge volcano into a volcanic powerhouse. The result is a dual energy system. The ridge pulls the crust apart, the hotspot pumps magma upward. Together, they create a volcano that erupts more frequently than almost any other on the planet, and the cycle is accelerating. Axial seamount has erupted 3 times in recent history: 1998, 2011, and 2015. Each event followed the same unmistakable pattern. The caldera floor inflates as magma fills the reservoir beneath. Pressure builds, the crust fractures. The eruption releases millions of cubic meters of lava, and the floor deflates again. Scientists learned to read this rhythm. They measured the uplift in meters, tracked seismic swarms, and predicted eruptions with shocking accuracy. In 2015, researchers forecast the eruption within weeks of when it actually occurred. But the current cycle is different. The inflation rate has surged beyond anything recorded in the previous episodes. The caldera floor is swelling faster, the pressure is climbing higher, and the timeline is compressing. What once took years is now unfolding in months. In January 2026, monitoring systems at axial seamount began registering anomalies that alarmed even the most experienced volcanologists. Pressure sensors embedded in the seafloor reported vertical uplift exceeding 2.4 meters, the threshold that preceded every past eruption, but the numbers kept rising.
Seismometers detected thousands of microquakes, a seismic heartbeat that intensified with each passing week. Fiber optic cables stretching across the caldera recorded temperature spikes and deformation patterns that matched the final stages before rupture. This is no longer routine volcanic behavior. This is a system on the edge of catastrophic release. The Ocean Observatories Initiative, an NOAA-funded network of deep-sea sensors, has transformed axial seamount into the most closely watched volcano on Earth. The system includes seismometers, pressure gauges, hydrophones, and fiber optic cables woven across the caldera floor. Every tremor is recorded. Every millimeter of uplift is measured. The data streams in real time to research institutions across North America. What the sensors reveal is staggering. The magma reservoir lies just 1 to 2 kilometers beneath the seafloor. Billions of tons of molten rock are being injected into this chamber, physically lifting the ocean floor like a balloon inflating beneath a concrete slab. The uplift is not uniform. Some sections of the caldera are rising faster than others, creating fractures that could trigger collapse. Scientists have calculated the critical threshold based on past eruptions. When the floor rises beyond 2.4 meters, the crust can no longer contain the pressure. The rock fractures. Magma finds a path to the surface. Current readings have already exceeded that mark. The question is no longer if the volcano will erupt. The question is when and how violently the release will unfold. But this was only the first warning. When a submarine volcano erupts, there are no ash plumes visible from shore. There are no glowing rivers of lava to photograph. But the energy release is no less catastrophic. Magma at temperatures exceeding 1200 degrees Celsius meets seawater at 2 degrees Celsius, triggering violent steam explosions and chemical reactions that can be detected hundreds of kilometers away. The eruption itself is only the beginning. The caldera walls at axial seamount are fractured and unstable. Decades of volcanic activity have weakened the rock, leaving sections precariously balanced. When the next eruption begins, the sudden emptying of the magma chamber could destabilize the entire structure. If even a portion of the caldera wall collapses, millions of cubic meters of rock and sediment will cascade down the seamount's flanks at speeds exceeding 100 kilometers per hour. The debris flow would obliterate everything in its path: marine ecosystems, monitoring equipment, and any infrastructure unlucky enough to lie in the zone of destruction. And the ocean itself would respond. Most submarine eruptions do not generate tsunamis. The water absorbs the energy, dissipating the force before it can travel far. But a collapse-triggered landslide is different. When millions of tons of rock displace seawater, the ocean has no choice but to move. The resulting tsunami would not rival the giants born from megathrust earthquakes, but it would arrive fast. Models suggest wave fronts could reach the Oregon and Washington coasts in 45 to 60 minutes, giving coastal communities minimal warning. Evacuation protocols exist, sirens are in place, but the timeline is unforgiving, and the signs were already spreading. The threats from axial seamount extend far beyond the immediate blast zone. Beneath the Pacific, a vast network of fiber optic cables carries more than 95% of all intercontinental data traffic. These cables connect continents, support financial markets, and enable emergency communication systems. A single severed cable can disrupt entire regions. If the eruption or subsequent landslide damages even a few of these critical lines, the consequences would cascade across the globe. Internet outages, financial system failures, emergency services unable to coordinate across borders. The infrastructure that powers modern civilization is fragile, and much of it runs directly through volcanic hazard zones. Engineers have warned about this vulnerability for years, but the sheer scale of the network makes redundancy difficult. Some cables are armored, others are buried, but none are truly safe from a major seafloor event. The economic cost alone could reach billions of dollars within hours.
Magma interacting with seawater does more than create explosions. It generates massive hydrothermal plumes, clouds of superheated mineral-rich water that rise hundreds of meters above the seafloor. These plumes alter ocean chemistry, disrupt marine life, and create thermal anomalies detectable by satellite. During the 2015 eruption, sensors recorded plumes so large they changed the temperature and salinity of the surrounding water for weeks. Fish populations scattered, chemical balances shifted, the ocean itself was transformed. If the current eruption matches or exceeds past events, the plume could be even larger. Satellites equipped with infrared sensors will likely detect the thermal signature first, providing the world's first visual confirmation that the rupture has begun. But by then, the damage will already be done. What came next shocked even the scientists. In March 2024, a magnitude 9.0 earthquake tore through the Japan Trench, releasing tectonic energy equivalent to thousands of nuclear bombs. The event was catastrophic for Japan, but its effects did not stop at the shoreline. Seismic waves traveled through the Earth's crust, redistributing stress across tectonic plates thousands of kilometers away. The Juan de Fuca Ridge, already under tension from its spreading motion, absorbed some of that energy. Scientists detected subtle changes in spreading rates and increased seismic activity along the ridge system. Axial seamount, positioned directly atop this ridge, felt the shift. The connection between distant earthquakes and volcanic eruptions is not speculative, it is documented. After the 2011 Tohoku earthquake, volcanic systems around the Pacific Rim showed increased unrest. Magma reservoirs that had been stable for decades suddenly began pressurizing. Fissures opened, eruptions followed. The tectonic domino effect is real, and axial appears to be its latest target. For researchers monitoring the Pacific Northwest, axial seamount is more than a volcanic curiosity. It is a real-time stress indicator for the entire Juan de Fuca plate system. The same tectonic forces that drive axial's eruptions also power the Cascade volcanoes, Mount Hood, Mount Rainier, Mount St. Helens. But axial provides something the land-based volcanoes cannot: continuous high-resolution data from deep within the system. The seamount acts as a window into the mechanics of the plate boundary, revealing how stress accumulates and releases over time. What scientists learn here could save lives across the region, because axial's behavior is tied to the most dangerous fault in North America. The Cascadia subduction zone stretches 600 miles from Northern California to British Columbia. This is where the Juan de Fuca plate dives beneath the North American plate, creating the conditions for a magnitude 9 or greater megathrust. The last major rupture occurred in 1700, triggering a tsunami that reached Japan. The fault is overdue. Seismologists estimate there is a 37% chance of a major Cascadia earthquake within the next 50 years. When it happens, the ground will shake for 4 to 6 minutes. Coastal cities will be inundated. Bridges will collapse. The death toll could reach tens of thousands. Axial seamount's current unrest may be linked to the same tectonic stress building along Cascadia. If the seamount erupts, it could indicate that the subduction zone is entering a more active phase. The volcano is not causing the earthquake risk, but it may be reflecting it, and the seismic heartbeat is accelerating. Inside a monitoring station in Newport, Oregon, Dr. Sarah Chen stares at the screen displaying real-time data from axial seamount. The seismometer traces look like a cardiac monitor in distress, sharp spikes clustering closer together with each passing hour. She has studied this volcano for 15 years. She predicted the 2015 eruption, but this time, something feels different. The swarms are intensifying faster than any model predicted, she says, her voice tight with concern. We're watching the system destabilize in real time, and the timeline keeps compressing. Her team works in shifts now, monitoring the feeds around the clock. Every anomaly is logged. Every pressure spike is analyzed. They are witnessing something unprecedented, a submarine volcano being pushed to its breaking point by forces that began thousands of kilometers away. The Ocean Observatory's initiative has revolutionized how scientists study submarine volcanoes. Before these sensors were deployed, eruptions like axials went unnoticed until after they were over.
Now, researchers can watch the entire process unfold, the inflation, the seismic buildup, the moment of rupture. Hydrophones have detected over 8,000 microquakes in the past 3 months alone. Each tremor represents the fracturing of rock, the movement of magma, the groaning of a system under immense strain. The data is unprecedented. The implications are profound.
For the first time, humanity can observe the deep ocean's hidden power in real time. Maximum alert is not fear-mongering. It is a status based on measurable thresholds, historical patterns, and live sensor data. When scientists use this term, they mean the system has entered the range where eruption is imminent. Axial seamount has crossed that line. Every metric points to impending release. The uplift exceeds past thresholds. The seismic activity is intensifying. The timeline is compressing. This is not speculation. This is observation. Most of the planet's most powerful processes occur where we cannot see them. The deep ocean is a hidden engine of transformation, driving tectonic shifts, generating new crust, and reshaping the seafloor in perpetual darkness. For most of human history, these processes were invisible. Now, technology has given us the tools to witness them. But observation does not grant control. Axial seamount is no longer a scientific curiosity buried in academic journals. It is a high-risk volcanic system on the edge of catastrophic release. The pressure has been building for years. The crust has been stretched to its limit, and the forces at play are indifferent to human timelines or preparedness. From the abyss to the shoreline, the effects will be felt. Tsunami waves could reach coastal communities within the hour. Undersea cables could be severed, cutting communication across continents. Hydrothermal plumes could alter ocean ecosystems for months, and the tectonic stress that triggered this crisis may be building towards something even larger along the Cascadia fault. Stay informed, stay alert. The abyss is preparing to speak, and when it does, will we be ready?